Okay, so good morning once again. So in my first lecture on Fourier series, we discussed about the Fourier series of a function fx when fx is periodic and the interval is alpha to alpha plus 2l. So this is the Fourier series representation formula fx equal to a naught by 2 and etc. where a naught, a and b n are the Fourier coefficients. And the interval alpha to alpha plus 2l can be 0 to 2l, it can be minus l to l, it can be 0 to 2 pi, it can be minus pi to pi. And these Fourier coefficients a naught, a and bn, the formulas for these given by a famous mathematician Euler's, and these are the formulas for finding the values of Fourier coefficients. By finding these values, we can substitute the coefficients here and we can have the Fourier series representation of any periodic function fx. So in this lecture number 2, I would like to focus on some basic formulas that can help in finding these Fourier coefficients. So formula number 1, the values of say cos n pi. So it is minus 1 raised to the power n, where n is, hello, Hanji. So the value of cos n pi is minus 1 raised to the power n, where n is integer and n can have the value 0, plus minus 1, plus minus 2, etc. For example, if n is equal to m minus 1, then the value of this function will be equal to minus 1 raised to the power m minus 1, or if n is m plus 1, then again the value of this will be minus 1 raised to the power m plus 1. Okay, so n is an integer. It can have value 0, plus minus 1, plus minus 2, etc. Or it can be m minus 1, m plus 1, where m is integer. Okay, then we have sin n pi. So sin n pi is always 0 for n belong to integer. The value of sin n pi is always 0 when n belongs to integer. Also we have one more, that is a part of this was the b part of this, c part. We can have cos of 2n plus 1 pi by 2 is always 0 for every n belonging to integer, and the value of sin 2n plus 1 pi by 2 is always minus 1 raised to the power n for every n belonging to integer. So this is what we have, the basic formulas to be used. Formula number 2, that is even and odd functions. So it's very important to check whether the function is even or odd. The definition is, if f at minus x equal to fx, then fx is even. If f at minus x equal to minus of fx, then fx is odd. Example, so we have sin x. This can be written as sin, say here fx is sin x, so we'll find minus x. So sine of minus x, we know that sine of minus x is always negative, okay. So this is equal to minus of fx. So f at minus x equal to minus of fx, so function is odd, so implies sin x is odd, so this is odd function. Similarly, we have another example. Say let's take cos x. So here fx is cos x, we change x to minus x everywhere. So then we use the property of sine of minus theta, sine of minus x. It is positive cos of x. So this is f of x. So cos of minus x is positive fx, implies cos of x is even function. Now here we are using these even and odd concept. Why? Because in Fourier series evaluation we do face integrals of this type, say minus a to a of fx dx. So the value of this will be 0 if fx is odd. So when fx is odd, the value of this integral will be 0. And the value of the integral will be equal to 2 times 0 to a fx dx if fx is even. So if fx is even, then the value of this integral will be equal to 2 times 0 to a and fx dx. Okay, so frequently we will be using these formulas, these techniques. So here we discussed about, say, technique number 1, that is some formulas. Say the value of cos n pi will be used frequently and its value is minus 1 raised to the power n. The value of sin n pi we will be using frequently, it will be 0. Then we'll use the concept of even and odd functions. Okay, and when we identify that function is odd, then the value of this integral will be taken as 0, and the value of this integral will be taken as 2 times this if function is what? Even. Okay, next we have the third one, and the third one is, the third one, that is, we have this Leibnitz rule of integration. That is, if we have two functions u and v multiplied with each other, then we'll take one of the function as first function and second function respectively, and this rule is equal to u v1 plus u dash v2, not plus but there it is minus. Okay, so we'll go with minus sign here. So u v1 plus minus u dash v2, then alternatively positive u double dash v3, then minus alternatively, then it is equal to u triple dash v4 plus, and so on, where u dash means derivative of u with x, u double dash means double derivative of u with x, and so on. v1 means first integral of v with x, v2 means second integral of v with x, and so on. So this is called as a Leibniz rule of integration. Now how to choose u and v? So if u is easily differentiable function and whose differentiation becomes 0 after third order, fourth order, fifth order, or so on, then we choose that function as u. Okay, so u will be chosen as that function in which the derivative of that function becomes 0 after few steps. so that function should be chosen as u function. Generally we prefer algebraic function as u function, and the second function will be chosen as a v function. For example, let's take an example. Integrate x cube sine of x dx. We do face these type of integrals in Fourier series. Okay, so here we'll choose this as u function and we choose this as v function. So this is u function, this is v function, and we use the formula u v1 minus u dash v2 plus u double dash v3. Okay, because we know the fourth derivative of x cube will be 0, so we will go up to third order derivatives u3 and v4. That is, this will be equal to, now u is x cube, we use the proper bracket. v1 means integration of sine, so minus cos x, minus alternatively u dash derivative of x cube, so x cube का derivative 3x square. Then v2 means integration, double integration of sine, so this is the first integration, so the another integration of cos will be sine x. Then we have sine of plus u double dash, so u, this is u dash. Now what is the double derivative of this? This will be 6x, and v3 means integration of v2, so this become positive and this is cos x. Okay, then we have minus u triple dash, so this is double dash, so it is triple dash is 6, and v4, this is v3, so integration of cos is sine x. So this is by Leibnitz, or we simplify this, so this is minus x cube cos x minus into minus plus 3x square sin x plus 6x cos x plus, in fact this is minus 6 sin x. Okay, so that is the Leibniz rule of integration. Okay, then we have the fourth one, and the fourth one is the formula. If we have e की power alpha x cos of beta x dx, this type of product function in which both functions are either one of the function is exponential, second function is trigonometric. So we don't have algebraic functions, so we cannot use the Leibniz rule of integration here. Okay, so here we have to go with integration by parts, but when we solve the application oriented problem, we don't have the time to find use integration by parts, so we'll use the direct formula. So it is e की power alpha x bracket start denominator alpha square plus beta square, right? Then we have alpha cos beta x plus beta sine alpha x. So this is the first formula, and if we have sine beta x here, okay, then it is e की power alpha x always outside, alpha square plus beta square here, alpha sine beta x minus beta cos alpha x. So we will use these formulas. Okay, let's take an example on this. So example, we have integrate e की power x sine of 2x dx. Okay, so this example, then we have this formula. So here the coefficient is 1, so here the coefficient is 2. Okay, so we have alpha is, so here alpha is 1 and beta is 2, and this is sine, so we'll use the formula e की power x, right? And in bracket we have 1 sine of 2x minus 2 cos of 2x divided by 1 square plus 2 square, and this comes out to be e की power x bracket start. So this is sine of 2x minus 2 cos of 2x divided by 1 square plus 2 का square. This is equal to 5. Okay, so thanks for listening. Okay, in next lecture I will discuss about problems on Fourier series, how to find the Fourier series of a function. So because these were the shortcuts that can be used in solving the Fourier series coefficients. Okay, so here we'll be having examples on finding Fourier series representation of a function. Then we discuss the half range Fourier series, etc. Thank you.